So yesterday we reviewed how to combine surface area and volume using real-world context, and today we're going to look at volume of shapes that are within other shapes, and just kind of combining what we've already talked about in class when it comes to removing them, similar to how we did with shaded regions a few modules ago. So we're looking at an insulated box, and it's made up of a larger cube with a hollow inside that is a right rectangular prism that has a square base. They have three parts they want us to do. One, to calculate the volume of the outer box. Two, to calculate the volume of the inner box. And then three, to determine what would the volume be of the outer shell if the inner box was removed. So if we are thinking about volume of rectangular prisms, then I do know that I have to find the volume of the outer box using our volume formula. So what is that if I look at my star chart? I see that it's volume equals area of the base times height. Well, if we are looking at the outer box, I know that the base, right, is also a square shape. And I know that because it is calling this prism a cube. They're also saying that it has a square base. So I know if one side is 24 centimeters, that this other side also has to be 24 centimeters. So let me just redraw it over here. It doesn't really look like a square. And I know that the area formula for this square is base times height. And so I can go ahead and substitute 24 times 24, and let's see what we get when we multiply these two together. Right, finding the area of the square. Here's our placeholder, adding right to left, and it is 576 centimeters squared. So this is big B, right? This is the area of the base. So I can go ahead and go back to my volume formula and substitute that in, 576. And then the height of our cube, how tall it is, I hate that it's doing that, is going to be based off of what else I notice in this picture. So I also see that this rectangular prism is also the same height of 21 and 1/4, which means if it is inside the cube, it has to be the exact same height of the cube itself. Oh my goodness, why is it doing this? Which is 21 and 1/4. And so I could leave it as a fraction, but I do prefer to write my fractions as decimals, which I know is 21.25. And so we can go ahead and multiply that as well. Given that it is such a lengthy number, I'm going to go ahead and just use my handy dandy calculator to save some time. And we see that the volume is 12,000. So here, let me write this down. The volume is 12,240 cubic centimeters. So that is the volume of the outer box. Okay, now they want us to calculate the volume of the inner box. So now I'm looking at this inner rectangular prism. So let me clean up my picture really quickly. And so again, I know the volume formula is area of the base times the height. I know that we have a rectangular prism inside our cube that also has a square base. So that means if one side is 18 centimeters, the other side is also 18 centimeters. So if I just redrew it to visually see it over to the side, I can also find the base and height by multiplying 18 times 18. So over to the side, this one won't take so long. Placeholder 8, 1, adding from right to left, 324. So the area of the base, right, big B, let me just put big B here, is 324 centimeters squared. So I know I can substitute that into our volume formula. And now I just need to find the height of that rectangular prism, which is the exact same height as what we used for before, of 21.25. So once more, if I use this calculator to kind of speed up the process, I see that the volume is 6,000. Let me write this down in a new color. Ooh, I'm running out of space. The volume, let me just move this down, is 6,885 cubic centimeters. So let me just move that out of the way a little bit. It is not moving down. There we go. So the volume is 6,885 cubic centimeters. This is for the inner box. So if I scroll back up and look at our boxes, we are thinking about question 3, which is telling us to find out what the volume would be if the inner box was removed, so just the outer shell. So if I go ahead and shade in, we are looking at all the space that is surrounding the rectangular prism but does not include it. So this makes me think of shaded regions when we had to take out a two-dimensional shape to be left with whatever was on the outside of that smaller shape. And so if I'm removing something, I remember that to remove or to take away is to subtract. So I'm taking the outer box. Now I could take and draw the outer box if I wanted to, but I think it's going to take me a little too long to do that. Minus the inner box will get us the outer shell, right? The leftover, the piece that is the space that is being taken up that is surrounding the rectangular prism but does not include the rectangular prism. Well, luckily, I already have the volume of the outer box. It is 12,240, and I just found the inner box, which is 6,885. So I know I need to subtract and take away that volume of 6,885 to see what is left over. So I'm going to go ahead and do that over to the right because we have to borrow, lining up our numbers. 0 minus 5, I can't do that, so I need to borrow. Some of us are still accidentally subtracting that even though we need to borrow. 3 minus 8, I can't do that, so I need to borrow again. 13 minus 8 is 5. I need to borrow again. 11 minus 8 is 3. I can't do this subtraction, so 11 minus 6 is 5. And so I see that the outer shell, or if we wrote a complete sentence, the volume of the outer shell is 5,355 cubic centimeters. So this is what our topic is going to be today. You are going to be seeing different rectangular prisms within another rectangular prism, and we are going to find both the outer and inner volume, and then we are going to remove the inner box using subtraction. So we're going to go ahead and practice a couple more on our own before doing the exit ticket.